be till you got, like I said, if you got a specialized team that can do bore scopes and know what they're looking for, they come in and do a bore scope on the engine. You get GE involved, coming in and do the bore scope, but it needs to be looked at. And you're at too high of a risk that something could have happened to the compressor section through there, so it has to be investigated. You always do a bore scope. The purpose of the high pressure turbine. What are we rotating? Wait, in the compressor.
Compressors.
Remember in that one illustration we saw? In this picture right here, we had the compressor, and then this was your high pressure turbine, but there was no shaft. Okay. In your application, the shaft connects both the high pressure turbine and the compressor. And so by maintaining fuel flow across here and this airflow, the rotation of the high pressure turbine operates the compressor section. So it makes it self-sufficient at that point. And this is where, when we're talking about the turbine cycle as compared to a reciprocating type engine, we're doing all 4 cycles through here. But this was the only working cycle in a reciprocating type engine, where in a turbine, I can make one revolution, one complete rotation of the rotor, and I've done all 4 steps. So this is when they talk about efficiency of a gas turbine. It's because I'm doing everything with one complete revolution of the turbine. The fact that I keep the combustor lit and a flame going all the time, I'm not repeating this over and over and over. I don't have this issue with expansion gases and abnormalities that can occur in a constantly, igniting fuel source. This is ignited through here. It maintains ignition. It maintains a stable flow through here. We'll cool it with the CDP air, keeping the flame centralized through here. Low impact on the high pressure turbine nozzle. Everything remains good. And like I said, this is when I talk about high efficiencies on, heavy duty turbines or aircraft engine turbines. It's because we have the ability to do all 4 cycles in one simple rotation through here. All right, combustor section. In the reciprocating type engine, we had valve located in the piston. And so when the piston was in a downward stroke, the valves would come open, allowing fresh air to be pulled into the piston chamber, and would also inject fuel into the piston head. And as the piston started to make its upward through there, the valve would close off, and then air become, and we had an air fuel mixture at that point. In our turbine, what we're doing is we have the constant pressure, just like you have with the full stroke on the piston. That's what's occurring here. We have a constant pressure here coming out of our high pressure compressor. The only difference is we're not adding fuel in this process of compressing the air. We're taking the constant pressure and adding the fuel through our nozzle here. Okay. So I still got the same situation. I still got a controlled amount of pressure coming out of my high pressure compressor, and I got a specific amount of fuel that I will apply because I'm measuring the pressure here. I'm measuring how much pressure and the temperature of the air through here. And that tells me that, hey, I need this much fuel to be able to maintain combustion and the speed, my high pressure turbine through here, and the output capability to push the power turbine. So this is what's going to be handled when we look at the fuel system, looking at the metering of what's going on in the turbine itself through here. Now, in the combustor, as I mentioned before, a lot of you have worked on heavy duty type turbines, and something that's very common in heavy duty turbines is they use this can style system. And so, depending if I had 8 combustor cans or 10 combustor cans through here, then you typically had a fuel nozzle per combustion chamber through here. So if I had 8, I would have 8 fuel nozzles. If I had 10, I would have 10 fuel nozzles. Now, the problem that you have through here is if one of my fuel nozzles is giving me problems, or I got an instability through here, that's a big section or a big void in that temperature pattern. You got to remember, airflow is moving in a spiral direction. It's circulating around the turbine as it's passing through. So it's making a circular motion. And so if one or even more of my chambers are giving me a problem through here, my temperature across here can drop significantly. And so as this mixes together through here, coming out this side of my turbine through here, my temperature pattern is going to be altered. It's not going to be real stable through here. And so I may try to compensate through other chambers, and that can cause some premature damage to my high pressure turbine nozzles and blades themselves, and it can cause premature damage in the combustor cans. So like I said, this was the beauty about this from a mechanical standpoint. It's really easy to come into a can system, open up the casing on here, take one of these combustor cans out, replace it with another one, close the casing back up, and you're back in operation. But the problem you have here is these have a short operating life. They're about 10,000, a little bit more hours, depending if you're running liquid fuel or gas fuel. But you usually get premature structural cracks on the support pieces through here and where it's anchored through here. And like I said, it's a big void. Should one of these give you a problem, my big temperature, I get a big shift in my temperature pattern through here, and that will compromise the output capability of the turbine. What you have is, well, as explained earlier, it's an annular combustor. And so if you notice on here, it's got the same shape as the combustor, the can combustor. But instead of being individual cans on here, this is just like one great big can. And so on your application, instead of being limited, like if you had 8 combustor cans or 10 combustor cans to 8 or 10 fuel nozzles, you have 30 fuel nozzles, and they're very close together. And so you're talking within a couple of inches of each other, and they go all the way around the back side of this chamber through here. So on this side right here where the circle is, this would be where your fuel nozzle is coming into the actual combustor can. Here you can see it. This is your combustor can. So my nozzle's coming in through here. This is my gas manifold, liquid manifold, kind of what you got coming into your system through here. In your case, you have both liquid fuel and gas fuel capability. But this is your combustor can. And if you see here, you got air holes and ridges on the can. You can see a better view of it. But see all the cooling holes that you have through here? As air comes through here, this is my P3 air. This is my compressor discharge air coming off my high pressure compressor. It's blowing across here. On the outside of the combustor, you have these kind of like ridges. And on the forward side of the ridge, let's see if I got a better piece. Yeah, here you go. See how you got these humps through here and these holes? The CDP air is going to come across here, hit against this ridge, but because my hole is on this side through here, or we'll use this one because you can see it a little bit better. As the air hits against this, instead of going up and around through here, I got a hole right here. So it's going to take the least path of resistance. And so this is going to force the air inside my combustor. Okay. I also have CDP air that's going to come through this inner liner through here and push across through here. So inside of here's where my flame is. My nozzles are up inside of here. Can't see it too well in this picture. My nozzles up and through here. My airflow nozzles are right back there. But coming through here, I got air also being forced on the inside of the combustor. And again, I got holes through here as I hit against these raised lips through here. Kind of see it better through here. Instead of deflecting and going around it, it's going to go through the cooling hole. And so what that means is you got this crisscrossing, air inside going out and air on the outside coming in, and it crisscrosses back and forth all the way up and down the combustor shell through here. And so that keeps an even temperature on the combustor liner itself. Also, the pressure of the air coming in and the angle that the air is coming in through here, as it blows across here and on this intersection blows through here, the flame that's coming out of the nozzles here is going to be kept right here in the center of the chamber through here, and it's going to keep it stabilized. So it helps with the flame shaping coming out through here. Now here, if I have one of my nozzles start to act up, they're in such close proximity that this and this one would compensate for any temperature variation caused by the loss of this one. And so these would compensate, and you're not going to see the temperature variation that you have with a can combustor. And so you're actually able to maintain, like this is something that's more susceptible to liquid fuel. Liquid fuel has a tendency to coat the nozzles and sometimes plug the orifice holes. You can see the small holes. These small holes is where the fuel is coming out through here. And so liquid fuel has a tendency sometimes with the hot surfaces through here, if it's still wet after it's shut down through here, the liquid fuel kind of dries on here, starts causing coking to form, and that causes a deflection in the flame pattern through here. Or it may cause a lower temperature flame to be produced because I got some of the nozzle portion blocked through here, and I'm not getting as strong of a flame pattern that I might be coming out for the other ones through here. But like I said, we're in such close proximity with all these, I'm able to maintain stability across. So it gives us a lot longer life on the combustor, a lot better heat dissipation through here. We got about 30,000+ hours of operation with a combustor section before you have to worry about doing a hot section change out. The only downfall is, if you noticed on here, this is a circle. And so my shaft from my high pressure compressor is coming through here, going out, and my high pressure turbine is on the other side. And so the only way to get a circle off of here would be to pull the shaft apart. Remember, this shaft is in two pieces. So this is what you're seeing here is a spline piece. This is coming from the end from the high pressure compressor. So the high pressure turbine is going to have a shaft that slides over this. It's going to be more of a female piece that will slide over this spline piece through here, and it's press fit together and it becomes one shaft. But it is a two-piece shaft for that forward shaft for your core engine through here, but it passes through the combustor liner through there. Now, not so much on this one. This was a used combustor that was in the shop that we took a picture of. But if you notice on this one, remember I told you on the high pressure turbine nozzles and blades that we had a ceramic coating to protect the surface, the metal surface, to give it a longer life on the blades. Okay, we're doing the same thing with the combustor section through here. The internal liner through here is a ceramic coated, and that's why you're seeing it white through here. Now, this is good in that it gives us a longer life on the combustor. Something you have to be careful about when you're doing um, a bore scope under here. It's quite possible to have a crack in the ceramic and it not really mean anything other than that the ceramic's cracked and it has a base metal and there's no damage beyond the actual crack in the ceramic. Uh, if you haven't done bore scope, the bore scopes have multiple tools that you can use to pick at the crack or measure the crack, the depth of the crack to see if it's penetrated, if the crack's actually going deeper than the surface indication through here. But like I said, a lot of times, the only problem with ceramics